Welcome back. So today we're going to be doing lecture number 21, which is Special Relativity Continued, with a little bit of General Relativity at the very end. Now, last time we talked about time dilation and how the measurement of time in one frame is different than the time measured in a frame that is moving relative to that first frame. Well, if the measurement of time is different, what about the measurement of distances? Are distances the same? Now, in the very beginning of the last lecture, lecture 20, I did a little demonstration that showed that they are not the same. Well, how might we do that a little more quantitatively? Well, let's imagine that we've got some object, let's say some meter stick or some stick of some length. Now, in my frame of reference, I'm the one holding the stick, so the stick is at rest with respect to me. We'll call that length the rest length. So when the object, the length that we're measuring, is at rest with a frame of reference, that frame of reference will measure what is called the rest length. So here we have a person holding some stick. Let's say that the length measured by this person is L naught. We'll refer to that then as the rest length. Remember, the rest length of an object is the length that the object has when it's measured at rest. Now, let's imagine that a frame is going to move past this and measure the length of this. Let's see if that frame measures a different length or the same length. Now, let's imagine we have another frame of reference, say a runner, who's running past this stick at some velocity v. Now, let's consider two events. The runner passes this end of the stick, we'll call that the first event, event A, runs past and then passes the second end of the stick, we'll call that event B. Now let's see if we can figure out how much time occurs between these two events. Well, who measures the time? Let's say that both individuals, both frames of reference, measure the time between the event A, when the runner passes the first end of the stick, and event B, when the runner passes the second end of the stick. So we must assume that both of these are carrying a watch. Let's say that this person has a watch. So the runner has a watch. The runner then has the watch at event A, and then has the watch at the event B. So the runner only needs one watch. One watch will be at both events A and B. So what time does the runner measure? Well, if the runner measures the time between two events with a clock that is at both events, the runner must measure the proper time, delta t naught. Now, for the person holding the stick wants to measure the time between event A and event B. So, to have clocks that are stationary with respect to the person holding the stick, this person must have one clock at event A and then one clock over at event B. So the person holding the stick will measure the time interval onto the difference between two clocks. So this person must measure the dilated time, delta t. Okay, great. Now, what do we know? For the person running, well, let's look at the person holding the stick first. The person holding the stick sees the runner moving at a speed v, running a distance L naught in a time delta t. So the person holding the stick will say that L naught equals V delta t. In other words, delta t equals L naught over V. Now, what about the person running? Will the person running assume that the stick has the same length? Well, perhaps not. We're not sure. Let's just say that the person running will measure a length L. So the person running measures a length L as this person sees the stick as going this way at speed v for a time delta t naught. So the person that's running will say that the stick travels a distance L at a speed v for a time delta t naught. In other words, delta t naught is equal to L over V. We know from last time that delta t is equal to gamma delta t naught. Now if delta t is L naught over V, and delta T naught is L over V, we get L naught over V equals gamma L over V. Multiply both sides by V, and the V's cancel. Divide by gamma, and we have L equals L naught over gamma. There we go. This result is called length contraction. Very, very good. Let's stick some numbers in here and see what we get. Let's imagine that this person is actually holding a meter stick, so that the rest length will take to be 1.00 meters. Now let's imagine that the person going past this meter stick is moving at 2.70 times 10 to the 8th meters per second. In other words, divided by 3 times 10 to the 8th meters per second, we get a factor of beta that's 0.900. This person, let's assume, is moving at 90% the speed of light. Again, not your ordinary everyday sort of motion. What do we get? Gamma is 1 over root 1 minus beta squared, which turns out to be 2.29. With L equal L naught over gamma, we have L is 1 meter divided by 2.29, or L is 0.436 meters, or 43.6 centimeters. Whoops, that should be centimeters. 43.6 centimeters. In other words, about this long. So the meter stick appears to shrink to less than half its original length. A very, very considerable change. But keep in mind, this only occurs because we have an extraordinary speed, 90% the speed of light. Now let's go back to the astronaut in the rocket and how we measured time. I want to mention one more thing about that. Okay, when we have the rocket and the Earth, if we look at the rocket's frame, and the Earth is basically moving this way at some velocity v, and the person in the rocket measures a time interval on the clock in the rocket, then the rocket measures the proper time, and the person on the Earth will measure a longer time. So the person on the Earth thinks that time is moving more slowly for the person in the rocket. But if the person on the Earth measures the time between two events that are stationary with respect to the person on the Earth, then the person on the Earth measures the proper time. And the person in the rocket would need two clocks, say one sticking out way in front of the rocket and another one way behind the rocket, to measure the time interval between those two events, if the events were stationary with respect to the Earth. In that case, the person on the Earth would measure the proper time, and the person in the rocket would see the person on the Earth moving more slowly, having a longer time, moving more slowly. This is very, very strange. The person on the Earth thinks the time is moving more slowly in the rocket, while the person in the rocket thinks the time is moving more slowly for the person on the Earth. How is it possible that both of them can think the other is moving more slowly? Well, there's a very important idea that we need to talk about, and that is the idea of simultaneity. Sorry? Simultaneity. In other words, things being simultaneous. Remember I mentioned that if this person is going to have multiple clocks down here, they have to be synchronized. In other words, they have to read the same time at the same time. In other words, they both have to read, say, 12 o'clock together. In other words, this person needs to think that those clocks are synchronous. In other words, they read 12 o'clock simultaneously at the same time. They need to read 1 o'clock simultaneously. Well, there's an inherent problem with that. Let's think about that for a minute. The question is, how will someone know whether two events are simultaneous or not in their frame of reference? Let's imagine that we've got a person standing on the Earth and two events occur. Let's say these two events are two bolts of lightning. So here's the person and two bolts of lightning come down. So we've got one bolt of lightning over here and one bolt of lightning over here. And let's say that they both occur, they occur at these 2 points, say point A, and this one occurs at point B. Now, it just so happens that this person is standing right in the middle at the midpoint between those 2 points. So let's say right equidistant from A and B. Now, how would this person know if these 2 events were simultaneous? Well, when they occur, they both send light waves toward the person. If those light waves reach the person at the same time, keep in mind this person is standing at the midpoint, if they reach the person at the same time, then this person could say those occurred simultaneously. In other words, the amount of time that they occurred before the light reached there was the same, so they occurred simultaneously. Now, what if event A occurred before event B? Well, in that case, like this, light starts coming from point A, then B strikes, light starts coming from B. Well, the light from A will reach this person before the light from B. So this person could say event B occurred before, event A occurred before event B. On the other hand, if B occurred first, light from B starts coming over, then light from A starts coming over, the light from B will reach the midpoint first, and so the person could say, oh, event B occurred first. So that seems like a very, very reasonable way of being able to say things are simultaneous, or this event occurred before this event. Make sure that you have someone located at the midpoint between the 2 events, and look at the light coming from those events. Which light gets there first, or do they get there at the same time? Great, that seems like a very reasonable way of defining whether things are simultaneous. Now, let's consider a frame moving relative to the Earth. Let's say we now have a train car on the Earth that's moving to the right at some speed v relative to the observer on the Earth. And now let's imagine we have these lightning bolts. So the lightning bolts come down, they strike the front and the back of the train, but let's imagine that according to the person on the ground, they occur simultaneously. In other words, we've got these events striking the front and the back of the trains simultaneously according to the person on the ground. In other words, what does that mean? Well, let's imagine the lightning bolts come down and they burn a spot, both at the back end of the train and the front end of the train. So the person in the train and the person on the ground can always refer back to where those events actually occurred in their frame of reference. This person is centered between these 2 events. This person would certainly say they're standing in the middle of the train, centered between those events as well. The light from these 2 events come toward each other, and they meet together at that point right there. So the person on the ground will say, yes, those events are simultaneous. However, what about the person on the train? The events occur, but the train continues to move to the right. As the light comes together, the train moves to the right. The train, let's say, has moved over to this position over here. Let's say the train has moved over here by the time the light waves from the 2 events have come together and meet here. We know that those waves meet at that point, so that this person says they're simultaneous. Well, this person says, no, they don't come together at the midpoint. They come together way over here. This ray from the front has already passed this person by before they get together over here. So this person would say the light from the front got to the midpoint before the light from the back. So what does this person surmise? This person says those two events are not simultaneous. This event occurred first. This event occurred second. Very, very interesting. Two events that are simultaneous in one frame are not simultaneous in another frame. So the question I asked in the very beginning of the first lecture, where it was possible, when I did the demonstration of snapping my fingers, where it was possible for the distance between two events to be 0 in one frame and not 0 in another frame, it is possible for the time between two events to be 0 in one frame and not 0 in another frame. The time between two events is 0 for this person. In other words, this person would say those occurred at the same time. The time interval is 0. They're simultaneous. Where this person would say they are not simultaneous. There is a time interval between those events. Very, very interesting. Simultaneity then has an issue, or helps us understand what's going on with a number of these other phenomena. For example, what about length contraction? How does simultaneity affect that? Well, imagine that this stick is passing me by, and I want to measure its length. Now, obviously, if I want to measure this length, let's imagine I have my own meter stick and I'm going to measure it. I would have to compare both ends of this moving stick with my meter stick simultaneously. However, the person moving with the stick would not say that I measure both ends simultaneously. According to this result, the person that's moving with the stick would think I measure the front end and then I measure the back end. So of course I measure a shorter distance, perhaps 43.6 meters or whatever. Remember when we did this example before? The person with the stick would say that I am not measuring the correct length because I am not measuring the length, the front and the back simultaneously. I measure the front end first, and then after a time I measure the location of the back end. So I'm not measuring the ends simultaneously. The person moving with the stick would say, I obviously don't measure the correct length. So the idea, this difficulty with simultaneity, can also help us understand how we get different results for different experiments, like lengths of objects and things like that. Well, how does this affect the rest of physics? Are other results in physics affected by special relativity? Absolutely.